Okay, hello everyone. Good morning, good afternoon, or good evening, wherever you are. Thank you for joining this SimScale hands-on session on electronics cooling. Let's make a start and introduce this session. So first of all, I'll introduce myself and I'll introduce Matt. So hi, I'm Steve Lene, and I'm one of the application engineering managers here at SimScale. But the star of the show today is Matt. He's going to be taking us through the actual hands-on session demo. And Matt's a valued member of our SimScale application engineering team. He's got a mechanical engineering background and over 6 years of experience of working in the CAE industry. First of all, I'll give you a very brief introduction to SimScale. So who are we and what do we do? Well, we created the world's first cloud-based engineering simulation platform. What does this mean? Well, it means that through a web browser, you can do fluid dynamics CFD, solid mechanics FEA, and thermodynamics. And we're leveraging the capabilities of having a fully cloud-hosted system. So as you'll see in this hands-on session, all you need is a web browser to be able to conduct your simulations. So how do you get the most out of this workshop? Well, follow along with Matt. And to do this, you're probably going to want a second device or a second screen, and possibly an actual external mouse if you've got one. And what we'll be doing is we'll be using milestones so that you can follow along with Matt. And the simulation project will be split out so that there's milestones down the left-hand side of the application. And if you get lost during any of the steps or you miss a step, you can just jump to the next milestone and follow along with Matt. Please feel free to ask any questions as we go through using the questions functionality in GoToWebinar. I'll be manning the questions. So I'll ask Matt any questions that come in that are important. We can stop the presentation and answer those questions to the whole group. Or if it's more of an individual question, I'll answer that individually with you using the text. The great thing about this is at the end, you'll have a fully working simulation that you can always come back to. Okay, so that's all from me. I'll hand over to Matt now to take you through this use case.
Thanks a lot, Steve. So first, let me give a bit of a background on our on-hands workshop case. So we're going to be looking at a liquid-cooled, water-cooled IGBT module. Here you see the geometry on the right. The type of questions we're trying to ask today is, what's the temperature delta across this water jacket cooling these two chips? What is the operating conditions of the two chips given a certain heat load, a certain wattage load? Does the system provide consistent cooling capacity? So for instance, does the section on the left here operate at a warmer temperature than the section on the right? Where can we just improve areas? Perhaps the next step would be considering a different sort of heat exchange design here. We're going to be doing this in a step-by-step process with you following along in your own project. And at the end, we'll take a look at the results and learn how to post-process and really understand what kind of results you have and how to make design decisions from it. So there are really 4 major milestones here, and I will just touch on them right now quickly. The first one is getting your geometry ready for simulation. So we're going to actually be using a new beta feature called CAD mode. There we'll be extracting a flow volume as well as doing a geometry imprint operation and a few other things. Once our geometry is ready for simulation, we'll go ahead and set up and say, okay, let's define the design parameters and operating conditions. What this means, what kind of materials are we using? What are the heat loads? What's the flow rate, fluid, and so on. Lastly, we'll set up the mesh and go over some sort of a runtime parameters. So things like setting result controls, so you know once you have results, not that just you have results, but that they are very good and accurate and you can trust them. Lastly, we'll spend a good chunk of time in the post-processor learning how to visualize the solution. Now, let's go ahead and jump into the platform. Steve's going to help me out here and share a link to the project. So I'm going to tab out. Thanks, Steve. So tabbing over here, you should be able to see water-cooled IGBT transistors, EC Workshop. You'll see my name and image here, and this is a private project, so everybody can see this. I am going to pause here for a moment and just let everybody find this and navigate to it. What we're going to end up doing is selecting the copy icon here. So I'll give it about 10 seconds and then we'll go ahead and copy the project.
Yeah, just to confirm, the link to the project is in the chat of GoToWebinar.
Steve, do you think I should proceed? Probably, right?
Yeah, go ahead. If anyone's got any issues opening the project or any questions, please feel free to send a chat message or post a question using GoToWebinar. Otherwise, we'll assume that you're all here and carry on.
So let's go ahead and select the copy button here. What I'm going to do is actually just put a hyphen here and put my name. So I'll encourage you to do the same thing. So just add your name to it, and let's go ahead and say copy project. Now, once the project is copied, we'll go ahead and it'll automatically open and we'll be in the workbench. You'll notice I did touch on those milestones in the slides. We do see those on the left, and we have two geometries here. I'm going to spend a few minutes and sort of go over how to generally navigate the SimScale workbench. Right now, I am using an external mouse, just a typical one that would come with a computer. I have a scroll wheel, a left and a right mouse click. So to pan, I'm going to press down on the scroll wheel and move left to right. To zoom in, I will use the scroll wheel and scroll it towards me or away from me. And to orbit, I'm going to left click and drag. This should allow you to navigate the project. You can also select in the bottom right corner the view cube where you see the Cartesian coordinate system. So for instance, if I wanted to look the geometry from a front view. Right now, this project is in a solid render. I can change this, but for now I'm happy with it. And I'm going to actually select the IGBT cool system, not the one that says milestones. Okay, I think we should be ready to move forward here. And again, if you're having problems, please just say so and we'll slow down or show you another step. So the first step in running a simulation in SimScale is making sure that the geometry is simulation ready. What this means is I need to actually extract the flow volume in this case. You'll see in the top right corner, I have my geometry. I have one solid. However, I need a flow volume, right? So I can sort of see right down into the system. That's not good. That's not what we want. So I need to make some geometry modifications. I'm going to hover over IGBT cool system, and let's select edit in CAD mode. It is in beta, but it's quite robust. So let's go ahead and do this. All right, I'm in CAD mode, and it looks very similar, except on the top you see a ribbon of create, face, body, model, commands, and so on. I mentioned what I'm going to do is extract a flow volume, and we see this in the top left corner. Now this is actually an internal flow volume because the liquid, the water, is running through this solid geometry. So let's select internal. Now when I'm going to do an internal flow volume extraction, I need to select some seed faces, a boundary face, and we won't worry about exclude parts. What a seed face is it's a face where the flow actually comes in or out of the system. So for instance, I'm going to select here because we have, this is either an inlet or an outlet here. We have, it's an opening essentially. So that's a seed. Oh, I'm sorry, this is actually going to be, we're gonna do boundary faces. So this is a boundary face, like I mentioned, because it's where the flow is coming out. We're defining the boundary. The backside, this will be a boundary face as well. And a seed face will just be any face internal. So it's any face that the fluid will be touching. So if I sort of scroll in here, and let's go ahead and select the seed face. I'm just going to sort of arbitrarily pick inside the system here, this face here. So I've got my two boundary faces. I've got my seed face. I don't need to exclude any parts. I'm happy here. So I'm going to go ahead and select apply. At this point, you'll notice the tree has changed. So now we have a flow region as well as this part 2. The next step I need to do to create my geometry or finish prepping my geometry is actually an operation called imprint. What that is it's a surface split operation that can make sure the solid and fluid interface where the two touch are lined up and surfaces actually share the same surface area. So this is in the model section in the ribbon here. So let's go ahead and select imprint, and I'll select apply. This is all I need to do to set up my geometry. We don't have any errors. Our history tree here looks good on the left. So in the top right corner, I will select finish. What this is going to do is return us back to the workbench. Now, this is where sort of the milestone is important. So I do have my new geometry here. However, just to sort of in case you got caught or got stuck, we are going to use the flow region milestones geometry. So we're going to use this one. It was already prepped. We know it's imprinted and there's a flow volume extraction. And so we're going to stick to this. Now, we really already have milestone 1 done, but next we have to get ready and create a simulation. Hovering over the milestone geometry, I will end up selecting create simulation here. Now from here, we have to choose what type of analysis, what type of simulation we want to run. There's a lot of options here. They'll pretty much they're all possible for you, but in this case, this is electronics cooling. We will want to use conjugate heat transfer V2. Here, if you look at the description, we have heat transfer between solids and fluids at the same time. This is definitely electronics cooling. I know I have an aluminum piece and water going in here. So conjugate heat transfer V2, I'll go ahead and create the simulation. Now this is sort of the first time you've seen our tree on the left side, and the workflow is top to bottom. There's a lot of things to do here, but in this step to get to this milestone, all we're going to do is confirm a couple things here. So first, there's the standard interfaces. Now, I mentioned we had to do that imprint operation. What this means is there's 152 faces on the fluid volume, which is also touching the solid geometry. So there's basically the fluid volume and the case or the housing. There's 152 of those. They all line up perfectly. That's good news. And so we don't need to do anything there. Next, we have model. Now we always see a green checkbox here, but what this allows you to do is set the gravity vector for the system. This is primarily a forced convection scenario. Buoyancy shouldn't play a huge role, but we have the option to solve that physics, so why not? You'll notice I already mentioned the view cube in the lower right corner. You'll also notice the Cartesian coordinate system. So what I'm going to do is actually set minus 9.81 here because down on the screen is going to be the direction of gravity. I'll hit save here. At this point, we're really done. So if you got caught there, got stuck there, you can just go up to milestone 1 with geometry and go ahead and just select the geometry here, and we're all done. That's really the only step you do in this process. I will just pause for 1 moment and then we can move on. Okay, so to follow along further, let's select milestone 2, design parameters. What we're doing here is setting up sort of the nuts and bolts, right? So material assignments for both the fluid and the solid, boundary conditions, and so on. Let's go ahead and start. So under material, I know my fluid will be water. We do have a default material database. As an FYI, you can actually always generate your own fluid material. So you can, any of these you can edit, but for now, I'm designing this system to work with water. And so I will just left click and pick to define the water. Now you can click in the viewer or also select the flow region in the top right corner. Either would work fine. I'll select the save icon and we are all set. We are done the fluid definition and assignment. For solids, I'm going to assign this plate as aluminum. This is quite realistic as aluminum, of course, does not rust, and it's also a relatively good conductor. What's interesting here is we actually already select the second geometry here. So this was the last geometry without a material assignment, so we automatically selected it. Again, of course, you can edit the material properties, but I'm happy with this for now, so I'll go ahead and hit save. Now we have to define the boundary conditions. I'll go ahead and select the plus icon next to boundary conditions. And first, we are going to define the inlet. So let's select velocity inlet. I'm going to name this water inlet. And I do have to make a few changes here. Instead of in component form, I really actually want a flow rate. And instead of mass flow rate, I want a volumetric flow rate. So here we have cubic meters per second. And I will go ahead and type in 2E minus 5. The system is quite small, so using units of cubic meter per second, it's a relatively low flow rate. My supply temperature will be 20 C sharp, and now I have to select the face. I will end up rotating this. So my inlet face is actually going to be sort of, if you position yourself at the Y plus or the positive Y where it goes, this will be the face I want to select. The way you can think of it is you should be facing or looking towards the origin. I'll select here to assign my water inlet and hit save. Next here, I'm going to assign a pressure outlet boundary condition to the discharge side. So this will be pressure outlet. You'll notice it is in gauge pressure here, so we don't need to modify the zero pressure here. It's almost like it's just discharging like an open faucet, discharging to ambient. Select, again, left click to select, and I'm just gonna call this water jacket outlet. At this point, we've really just defined the fluid side of the system. Now we have to define our heat loads. Now, so the way I set up this model is I did not actually explicitly model the transistors. What we're going to do instead is use a heat flux boundary condition on these surfaces. So to add this boundary condition, I will actually just select wall because it is a solid wall. And here I'm just going to select 400 watts. Now for a temperature type, this will not be a fixed value. This will be an external wall heat flux. And instead of a fixed heat flux, it's just going to be a power. So we don't care about the area term. What we're saying here is this is going to be 400 watts. One thing to note with SimScale, very similar to other CFD programs, I'll select left click to select the two surfaces here. What this means, we're putting 400 watts into each of these surfaces. So the total heat going into the system is 800 watts. At this point, really the setup is done, but one thing that may not be completely accurate is right now we are modeling the system as if there is just no heat transfer to ambient. It might be smart to model it like that because maybe the system's working in a warm room, or maybe this is pressed up against insulation. But in real life, if this plate is warm, there will be some natural convection ambient to the air around it. You don't actually have to model the air around it. What we use is a convection boundary condition to approximate how much heat is lost to the rest of the system. I will model this just to have the simulation results be a little more accurate. And so let's add a wall boundary condition, and let's just name it ambient. Again, instead of that fixed value, this will be an external wall heat flux. Instead of a fixed heat flux, it will be derived. Here, this will be, I like the heat transfer coefficient of 10 watts per K meter squared. And for an ambient temperature, let's go ahead and use 20. What we're saying here is, let's assume the top face is 1 meter square. And let's assume I said ambient is 10 degrees, maybe it's a cold operating condition, and the plate happens to be 20. Well, we have a 10-degree delta, we have a 1 meter square, there's going to be 100 watts being discharged. So 10 times 10, there's going to be 100 watts discharging to the system. And so that's gives you sort of the background for what this actually means. For assigned faces, let's go ahead and start selecting. I'm going to grab pretty much all the side faces. And so there's 4 sides and then 4 chamfers. And I am going to select this top face as well. And I'm not going to grab the back face. So maybe this is mounted against a wall, and we really can't count on there being any conduction through that wall. So let's just use these 9 faces. I'm happy with this, and I'll go ahead and close this boundary condition. At this point, we have completed milestone 2. We've completely set up the design parameters and really are in good shape. I'm going to collapse this and just pause for 1 moment.
That's great, thanks, Matt. Just before you move on, we've had a couple of questions come in about the actual setup of the simulation here. And someone has asked whether we'll model the transient behavior of the IGBT, because in reality, obviously, the IGBT will be switching at a certain frequency. So what can you say about that for this simulation?
Sure. That's a very good question. With simulation, you tend to really just want to take the worst case. So here, steady state with both IGBTs turned on at 400 watts continuous, that's the problem we're solving for, and we'll understand what that performance is. If that performance is acceptable, we know we can really handle any kind of transient behavior.
That's great, thanks.
Is that it, Steve?
Yes, that's right, thanks.
Okay. Now let's move down to milestone 3. Again, if you got lost during the design parameters, no problem at all. Regardless, we're going to be moving into milestone 3. At this point, we are going to define the mesh and result controls. Now, let's go ahead and move down in the geometry tree to advance to result controls. These are actually optional. What they are is a sort of probe that will allow you to monitor the exact, it'll write out a CSV of exact data for specific critical areas in the model that you care about. I'm going to, a lot of times I like putting these on my heat loads. So I'll go ahead and select surface data, and let's grab an area average. I'll select the top of the IGBT here. And I always like to name these something smart, so I know as the run goes on, I can reference them, I know what I'm looking at. So this means every iteration, we are writing out the average temperature for each one of these surfaces. This is an average, so we look at all the cells. It's an area average. We take a look at the square area of each one of the cells and find what is the average temperature across this. We get a plot, and we can actually sort of judge convergence and not only understand, do I have results, but do I have results I can trust and results that are good, and understand if my solution can be trusted. One of the first things I'm going to be looking for is, okay, well, if my inlet is right here, does this IGBT operate at a cooler temperature than the downstream one? If that's the case, well, there's a higher chance I have failure down here. So I selected my surface data, and I'm happy with that. Now let's move on to mesh. Now we have already loaded a mesh here, and I did go with the default settings, but I'd still like to touch on this for a moment. So let's first of all, let me kind of repeat that. If you select mesh, you'll get the dialog box here. And if we click on mesh 1 fineness 5, we can say, let's create a new mesh. What I'd like to do here is step you through some of the properties and some of the things that can be changed. So first things first, this is the standard mesher. This is basically a default. It's a TET surface mesh with a hex core. And for the sizing, we will do an automatic sizing. So for instance, we're going to add mesh density around fillets or where there's smaller geometry. Out in areas where there's very large surfaces, but there's not a lot of detail, we will coarsen the mesh. You can modify the fineness with this slider. It goes from 0 to 10 with the default of 5. And I usually don't change the global settings here. I usually go with global 5 and then add density manually where necessary. We do automatically add boundary layers in places at the fluid wall interface. We use 3 with an overall thickness of 0.4 compared to the cells adjacent to it, and a growth rate of 1.5. These are all things I'm not actually going to touch or toggle on or off, but I would like to just touch on them to describe what they do. Moving on, we have physics-based meshing. Now, we actually have mesh at the bottom of the geometry tree because we're trying to sort of intelligently set up a good mesh for you based on all the upstream information, everything we already filled out ahead of time. So for example, we're going to add more mesh density to the fluid versus the solid. Solid conduction is very simple. You don't need a lot of density there, but here we have internal CFD flow. It's quite complicated, and so we're going to add density there. Next, we will also add refinement where there's boundary conditions, so our inlets and outlets, and we actually will calculate the hydraulic diameter and add a region refinement, several hydraulic diameters into the system. This is a hex core, as you can see, and I would recommend leaving this. Under advanced settings, we have a few other things. Small feature suppression basically helps you deal with less than ideal CAD. And gap refinement factor is actually sort of like a fluid gap system. So for instance, if I set this to 1, there would be at least 1 core cell through a channel. I'm not going to change any of these settings. What I will do is go ahead and select generate. You'll notice we have a few estimations. So we think this will take 30 to 40 minutes. I think we're overestimating a little bit here, but that's okay. We think it'll be between 4 and 6 million cells. Go ahead and select generate here. And instead of waiting, say maybe 10 minutes or so, let's go back to that mesh 1 fineness. We see it was 3 million cells. It took 14 minutes to generate. And a few things to point out here, right? So we do see those wall layers. and the number of cells through the channel here looks great. Overall, this is quite a bit of density. I'm happy with this, and we don't need to change it. So at this point, I'll pause for a moment, and please, if you have a question, feel free to ask it right in the chat. I'll give it a minute, and we will jump into milestone 4. Okay, let's expand milestone 4. The setup is done. We've done the mesh, we've done the result control, boundary conditions and material assignments done. Let's skip to the fun part, go down to simulation run, and let's go ahead and select the plus sign next to it. Again, we're using milestone 4 because I know this is set up right and you won't run into any issues. So here it's asking me to rename the run, and it's giving me a resource estimation. So it thinks this will take 55 to 83 minutes, and it will use between 30 and 40 core hours. Now, the great thing about SimScale is we let you run multiple simulations at once. So right now I'm just presenting from a laptop. It only has 2 cores. I don't have to worry about queuing simulations. I can get work done like I have 1,000 cores in my back pocket. Here, I'm going to say 20C supply and select start simulation. Now this gets kicked off and we'll run. We'll get a convergence plot in a moment. We'll be able to see the solver log and monitor other things as it runs. Now, if I want to do a boundary condition change or something like that, I can go ahead and do that and then submit again. I will show you that in a minute here. So under velocity inlet, maybe I want to see if I can get away with warmer water. So for instance, here we have the water is the same temperature as ambient, as the air, but maybe we can even supply warmer water. I'm not sure. Maybe there's enough convection to the rest of the room, and it's ultimately about what is that temperature on the transistor face where we have that 400 watts of heat flux. So let's go with a 25C here. I do want to touch on one other thing here just to really cover all the details. So under simulation control, we have a few parameters here. This is where you say, okay, run it for this many iterations, use this kind of hardware and so on. You'll notice an end time and a delta T here. Now, this is a steady state simulation. I made this ahead of time, a steady state. So what we mean by an end time of 1,000 seconds is this means we're going to be running 1,000 numerical iterations. By then, the solution should be very converged. That's actually a very conservative number. Usually the system converges much sooner than that. The delta T is really just at what increment. So if I were to put this at 2 and leave the end time as 1,000, we would only do 500 iterations. The right interval is how often do we want to save result data sets. There's almost no reason to change this from the default when running steady state. SimScale is actually smart enough that we write out temporary intermediate data sets. And so as the simulation is running, say it's halfway done, you can go ahead and take a look at the results anyway as it's progressing. Next is the number of processors. You'll notice the default is automatic. Now we give you access to a lot of computing power. We actually give you access to 96 cores with the professional license, as you can see here, and 16 on the community account. Now, just because you have access to all that compute power doesn't mean you should always use the biggest machine. There are sort of rules of efficiency at play and all. So what we've actually done is just automated this. What we're going to do is mesh it, understand the cell count, and then pick the machine that will get you a result as soon as possible. The max runtime is sort of a safety mechanism here. This means if after 1,000 seconds of clock time, sitting in your office waiting for the simulation to finish, if you hit this, the simulation will be canceled and it's a safety, right? Because we are running on the cloud, we wouldn't want a simulation that runs for maybe something goes wrong or you set up something wrong and it just runs for days, weeks, or even months. I usually actually set this to 36,000 seconds, 10 hours, but for now, I'll just leave this. Now, I made that boundary condition change, raised the supply temperature, but I never hit run. So let's go ahead and do that. 25C supply, and we can go ahead and hit start. So at this point, we're done milestone 4. Let's just give it one moment and we can start to go into post-processing and understanding the system. So let's expand finished simulation. We can go down to simulation runs, and you see here 2e to -5 cubic meters per second. I ran this yesterday. It took just over an hour, and we could take a look at a few different things here. I guess first of all, we can take a look at the conversions plot, and let's look at residuals. This looks pretty much like you would expect. So all the residuals for every degree of freedom, we have X, Y, Z velocity, pressure, and temperature starts at 1. And what you want to see is over time, these drop and flatline. There's not a lot of physical meaning behind these, but you do want to see this trend. And it is an indicator of a good simulation, but it should not be really trusted 100%. What I'm more interested in is those area averages I set up on the transistor solid interface. So the IGBT surface, first thing I want to do is look at temperature. Now you can actually see this changing over time. So it starts out really at ambient, and over time, it's sort of the y-axis is in Kelvin temperature. This is the average temperature. And we're writing out what the temperature is over time here. So obviously the black line is the one closer to the fluid inlet. So this one's operating at a better temperature. The transistor here will last longer, most likely. Here we have 306 Kelvin. Up here we have just around 311. There is some sort of bobbing a little bit to this graph, but it's important to keep in mind what the y-axis looks like. So we're between 110.9 and 111. So really just the noise is within a tenth of a Kelvin. Now this is about a 38C temperature on a water supply of 20 and an ambient room of 20. So there is a reasonable amount of heat up here. However, 38 in the electronics world is not bad at all. At this point, I think it's time to jump into the post-processor and have a look at our results. So let's select 2e -5 cubic meters per second. And we're going to say, let's post-process the results. Now, we are actually beta testing, sort of at the later parts of a beta test on our new post-processor. I'm really excited about this. What we're going to be using today is the new beta interface. So go ahead and select this. Keep in mind, in the bottom right corner, we can see we kind of have a job status and we understand what's going on. So a few things here. On a normal desktop solution for CFD, I would not be able to mesh at the same time I'm running simulations. And I wouldn't be able to be running 2 different simulations at once. I was already doing some post-processing here, but I think it's best if we sort of peel this back and start from scratch. So here, let's go ahead and hit the trash can here to get rid of this cutting plane. And let's go up and toggle the bulk calculator. Now, under the parts color, I can select here. Globally, we're looking at temperature. Instead of Kelvin, let's use Celsius. That makes a little more sense to me. And I usually tend to start with a bit of a basic sanity check. Well, the coolest part is that water inlet. Okay, that makes sense to me. The warmest section really is the plate where we have the heat flux, and it's the second one. That is consistent with the IGBT surfaces and area averages. We know that this second IGBT surface interface is operating at a warmer temperature. We see the max around about 40. That checks out with the average on that second piece of about 38. Now, one of the first things I do, although you don't have to, but I like to kind of check the energy balance of the system. Or for instance, here I'm interested, okay, I'm putting 800 watts into the system. How much is going to water and how much is actually going to ambient? There's a great way you can do this. So let's go ahead and add a filter. Let's add a cutting plane. And I'm interested in looking at the Y. So ultimately what I'm going to do here, just to give you a bit of background, I want to look at the outlet temperature, understand the temperature delta on the system. I know my volume flow rate, so I know my mass flow rate, and I know the specific heat of water. That you multiply those and that tells me joules per second, which is a watt, and I can understand the energy balance of the system. Now let's use the slider bar here to essentially get right close to the outlet and try to get a little closer. That looks good. Obviously, here we're still looking at velocity, but what I want to know there is what's the temperature. So let's go ahead and select temperature. And I could probe it, but what would probably be more accurate is if I get an average. So let's toggle on the bulk calculator. And I get a few sort of cutting. What this does is it gives me an overview for all the cross sections. It recognizes that the solid is a different part than the fluid. And here we have an average of 29.6. So that's about a 9.6 C delta. I'm going to very quickly tab over to a spreadsheet I have that I put together. So specific heat, 4,180 joules per kilogram per K. Delta is 9.6. Remember, at the inlet, I had 20 C. I did some quick math to get mass flow rate, and that means we have 800.4 watts roughly in the system. So what's that tell me of this system? Well, I really don't have to rely on convection, or there's almost no convection in the system. The great thing about water is it has extremely high specific heat, and there's really no heat going to ambient here. We're just relying on the water. What we can do is, if you weren't sure, if you doubted it, you could remove that external surfaces boundary condition, or if you knew you could rely on the room, you could actually reduce the flow rate, and that'll get you savings in a circulation pump and in moving water over time. So I know I have good results by now. I pass an energy balance sanity check, and my area averages look good and my residuals look good on my convergence plot. Let's understand the flow pattern, and I am going to use a cutting plane again, but let's understand the flow pattern through the water jacket. If we position this in the Z, and I actually want to look from the top down. So I will, for the orientation, I'm happy with Z, but I want to invert this. And I don't care about temperature anymore. I'm interested in velocity magnitude. Now I actually, it's a little confusing because I have two legends here and I know it's a little hard to tell what I'm looking at. So let's go up to parts color. If I toggle this off, and I should be able to, yeah, I'll just toggle it off for now. So here now I'm just looking at the cutting plane, and I'm going to select the top view here to help sort of organize this. This pretty much makes sense. I have my velocity on the way in. I see some peaks around the corner. I see some dead zones. Magnitude is great, but my next question is, I want to see direction. I'll turn on vectors, and this tends to get a little graphics intensive sometimes, and I will actually turn down the opacity. So I think I go with about 0.4. It's not very helpful when the vectors get stuck under the cutting plane, so I like to make it transparent. Now my scale factor needs to go way down. I'm going to try 0.05. And I actually like clamping. So the problem with the standard clamp is we scale the vectors based on velocity to the point where they're so small you can't even see them. I'm happy with the maximum clamp, but I actually want to bring up the minimum here. So here, this just allows me to have a better understanding and see where these vectors are. Now from here, of course, these are still too big. So instead of a scale factor of 0.05, I will select 0.01, whoops, it's 0.01. This is more like it. I'm happy with this. And now I need to increase the density. So for the grid spacing, instead of 0.02, let's try 0.01. That's still not really good enough. I may even actually 10x the density here. Okay. And let's try. Okay, so this is sort of a happy medium. So I ended up landing on 0.0025 for the grid spacing. Here we can start to understand how the flow goes around certain sections and changes direction. What I'm interested in here particularly is we may have some recirculation zones. What's that mean? Well, we actually have flow going in the opposite direction of the dominant flow direction. We see a peak here. Of course, the flow actually speeds up as it bangs in that corner, is forced to accelerate and go down the screen. And we see some vectors sort of getting stuck, and we have low velocity here. But I actually want to understand it and have a better understanding of what exactly is going on in this corner, in this area.
Sorry, Matt, can I just stop you there for a moment? We had a question come in. Somebody asked for a bit more clarity on what exactly the clamping does.
Sure, absolutely. So there's sort of a global minimum and maximum. Without clamping, there's a global minimum and maximum vector size in the domain. Somewhere in the system, there's a really large vector, and somewhere in the domain, there's a really large one. Here we're looking at velocity. So really what the system's seeing is anywhere there's a zero velocity, there's actually a vector size. It's just 0 in length, 0 meters, or you can't see it. What the clamping does is it allows you, it sort of exaggerates those low velocity areas. I know they're low velocity, I can probe them, but I'm still interested in being able to see and visualize the direction of the flow. Moving on, I need to make my vectors a little smaller. So let's cut that in half. This makes more sense. And I need to tighten up the grid spacing. Let's lose the 5 there, and let's keep going. Okay. So just to sort of clarify, I landed on a scale factor of 0.005 and a grid spacing of 0.001. What we end up seeing here is, for instance, in this top right corner, we do have a flow going in the opposite direction. Well, what this means is you're going to have high pressure drop through the system. You will actually, I guess, the good side of it is that you will have very good heat transfer here. However, this is just the areas that will cause the most amount of pressure drop through the system. Now, let's go ahead and turn off vectors here, and we can sort of move on. I do want to point out one last thing, and so I did just touch on the fact that chaotic flow usually ends up meaning you have good heat transfer. If we turn on the default region and actually map it to temperature, you'll see there's sort of a warm spot down here. And let's go ahead and turn off the clip. You see this warm section up here, and you may wonder why that is. Well, we have a heat flux there. We have warmer fluid, and if I turn the clip back on, I don't have a lot of interesting flow going on there. It's It's not changing direction. It's not a large gradient across the tube. It certainly is not fully developed flow, as you can see. So that's why you have a warm spot there. Let's go ahead and toggle off the cutting plane and look at how else you can use some more post-processing features here. Let's go ahead and add another filter. And here I want to look at an ISO volume. The main question I have here, let's grab a reference. I think essentially my mean velocity is roughly about 0.26 meters per second. I want to check that, so I'm going to use the inspection point and grab the center of this tube here. I wasn't too far off, let's say about 0.25 cubic meters or meters per second, excuse me. We can go ahead and shut off the cutting plane, and let's go ahead and drop in a filter. A lot of times I want to understand where's the global maximum velocity in the system. Now, I need to hide my geometry. So if I go in the top right corner, I'm just going to hide the default region, or let me actually just put it in outline mode here, wireframe. So I have some understanding, or maybe perhaps even translucent surfaces would be great. So I'm going to set the minimum and maximum ISO for velocity, and I'm interested in everywhere that's above 0.25 meters per second. It doesn't matter what we set the max bound. I can use something large like 1 meter per second, and I don't want to color the ISO volume by temperature. I actually want to color it by velocity. It's still a little too hard to see, so let's go back to wireframe. As I mentioned, you get velocity speed up. So the section you see through the middle of the tube here, that's just, you do have some partially developed flow. So the velocity is the highest in the middle of the channel. And if I bump this up, you're seeing here high velocity sections as the flow goes around corners. You do not see, you see the nice kind of boring flow here where there's that hot section. That's because, like I mentioned, there's not much going on here. Lastly, what I'd like to do, we're running a little long on time, so let's turn off that ISO volume. A lot of times I like to use a particle trace to visualize the flow through the system. So let's go ahead and add a particle trace. And I'm going to select the left view in the bottom right corner. This means I'm staring straight on at the inlet. I've already selected the pick position, so I'm going to be setting the seed for the particle trace. What this allows you to visualize is it's as if you're following the path of a single particle through the whole system. So let's click here. And I dropped in a 10 by 10 grid, and I have a default spacing here. I'm happy enough. I could tighten up the spacing of the grid, but I'm happy enough with how it looks. And I could probably, I could change the diameter of the size of these particle traces if I was interested, but really I'm okay with how it looks. Here we can see the flow, and you do see that gradient. So for instance, here in a single cross section, we have some flow that's going, say, 0.2 meters per second. We also have some flow going 0.33, maybe 0.35 meters per second. That gradient is what's causing the high amount of heat transfer. Now, lastly, this can also be animated. So I'm going to add a filter, and let's add an animation. And instead of an animation type of time step, I want to see an animation type of particle trace. The 300 steps or frames I'm happy with, I can live with, so I'll go ahead and hit play here. Here we see the flow going through the system, and we can understand the gradients and velocity. Steve, this is mostly what I wanted to share.
2 minutes left. If anyone's got any burning questions that you would like Matt to answer, please send those in on the chat. Otherwise, please feel free to contact us after this if you'd like to find out more. Okay, so it doesn't look like we've got any more questions coming in. So thank you again for that, Matt. That was absolutely brilliant. I really enjoyed following along with that. Oh, hang on a second. Oh, just some people saying thank you. So yeah, thank you very much. Thanks everyone for attending.